Okay. So, this is the last, almost the last whiteboard we have together, and we are specializing the Lagrange equation motion for elastic body. So we have to specialize these terms like this as a term. This is the A term of the Lagrange equation motion. We have a B term like this to be developed. And finally, this last forcing term, C. So up to now, we have developed this A term, and we found that supposing to introduce this shift function like psi n and the related coordinate, we can rewrite our dynamic problem by introducing T and E, and this dynamic problem can be specialized by expressing the kinetic energy here as a function of velocity and then as a function of the new variable. In this expression of the kinetic energy as a function of the new variable, we have to respect the concept that for any motion and for any velocity distribution, this quantity, the total kinetic energy, has to be a positive quantity. We can see clearly this positiveness of the kinetic energy here by the definition, because we have an integral of a positive function to be integrated, like rho by v dot b, and it is positive. The integral is positive for any kind of motion. So for any kind of motion means, in terms of the new variables, for any vector in engineering vector, q dot, for any q dot, we have to have a positive function. And since this function is a quadratic function, by means of this tables or matrix M, necessarily this matrix has to be positive matrix. And the positiveness of this matrix is just arising by the definition of positive matrix. A positive matrix here is positive if and only if for any vector A, when you take this quantity A transposed by A, capital A, and A again, you always have a positive number, okay? And this is just what happens here in the kinetic energy. You will have always a positive number, and therefore this is currently demonstrated that when you build this matrix is a positive by this definition, and is symmetric by its own definition here. Here, this is the definition, but it is only positive beside symmetric. Okay, so at the end of the story, the A quantity here, this is the A quantity is of this type, can be reduced to this, okay? Now I want to talk with you about the B quantity. The B quantity is essentially related to the concept of elastic energy as a function of the new variable Q, the vector Q. Okay, in order to define this quantity is essentially the total internal energy, and this total internal energy is equal to the integral on the body volume of the volume energy, which is also expressed like the product of rho by E, where this E is the internal energy per unit mass, and then multiplied by the density integrated, you have the total energy of the body, the total internal energy of the body. So now remember that we have as hypothesis, this hypothesis, we are currently expressing the displacement unknown as a summation, a linear combination of the new Lagrangian variable through this space function. And this space function, in the common application, in the common engineering application, are the finite element shape function, and therefore are function with this kind of property we recalled the day before yesterday, just here. Now, go back here and talk about this internal energy. We have to consider the following hypothesis for our problem. Excuse me. Okay. Okay. We have one hypothesis of elastic body. Elastic body means that if you want the stress tensor is composed by only the reversible part, only reversible contribution, and this reversible contribution in the case of elastic body is given by the rho by the derivative of the internal energy per unit mass with respect to the corresponding component of the strain tensor. Okay, this is the definition of elastic body. Okay. Second position, consider a linear behavior in a constitutive law point of view. What does it mean? This means that we are supposing that the stress tensor, the reversible part of the stress tensor, we are considering only elastic bodies, so only reversible transformation. So in this case of reversible transformation, if you have this further hypothesis, linear behavior, in the constitutive low potential view, point of view, we have that this is related to the deformation by a linear relationship like this. And this is also known as a relationship between a second order tensor with another second order tensor through a fourth order tensor, which is the tensor relating the stress with the strain in a linear way. So linear, elastic and linear, 2 points. So by these two hypotheses, we have an important consequence. And the consequence is this third point. Now try to expand the volume elastic energy in the sense that suppose that the total energy is the integral of the volume energy, rho E by definition, and expand as a function of strain. The strain, by definition, is 0 in the reference configuration. So imagine to expand this function in the neighborhood of your reference configuration. And therefore, you should have the following. You have an integral of this quantity in the undeformed configuration. In this case, you have a constant like E, and then you can expand this volume energy with a first order term like A, Ij, epsilon Ij, and a second order term like epsilon, for example, Ij B Ij. Please follow me in this theoretical point. Bij K L epsilon KL plus higher order term, this in dV. So what I'm doing, I am considering this quantity. This is E rho, the energy per unit volume. This quantity, as in the case of the elastic body, is function of only one tensor quantity. The tensor quantity is the strain. Everything, any kind of state-space variable, in the case of elastic body, reversible transformation, everything is a function of this tensor quantity, which is the deformation. So, in particular, the energy per unit volume will be a function of E. Okay? Okay. So, how can I imagine this function? This function is zero or is a constant. This constant may supposed to be zero. I'm saying that this may be zero. This should be zero because it's an arbitrary constant. But if you have a small quantity of strain, this strain will be transformed in a value of this internal energy. Internal energy is a function of the strain. And here we have an expansion. Is this expansion correct? Yes, it's correct. If you have a small strain, if you are studying linearized problem, this is absolutely correct. And you can control this expansion. Okay? So, now please combine these three elements. Combine 1, 2, and 3. And what is the result of this combination? The consequence or result of this combination on this point is very, very interesting. In fact, use the definition of elastic body, this here, and apply this definition on the definition of total internal energy. Okay. Before doing this, please, another comment. What about this coefficient B and A? Well, B and A, following the role of Taylor expansion, are something related to the derivative of the internal energy, the first derivative and second order derivative, okay, of rho E with respect to epsilon. It's something strange because we are considering epsilon as essential state-space variable for elastic solid transformation. In the elastic solid transformation, the only essential state-space variable is the strain tensor. Okay? And therefore, this quantity A, Ij, and Bij have necessarily the meanings of this here is the derivative of rho E with respect to epsilon Ij at zero deformation or reference deformation. This is a first order derivative with respect to epsilon. And this here, pay attention please at this point, this here is necessarily the second derivative of rho e, one time with respect to epsilon ij, and a second time with respect to epsilon kl, evaluated at zero deformation. A very, very strange quantity, but it's just a mathematical quantity. Introduced considering a generalized expansion, Taylor expansion. A Taylor expansion of the internal energy around in the neighborhood of an undeformed configuration. Okay? Now, apply this concept to the concept of elastic body. If you apply to the concept of elastic body, you have the following. You have that if elastic body, then rho e is equal to the derivative with respect to epsilon ij, this is the definition. Excuse me, I am applying this. Sorry. So we have not this. Excuse me. We have tau ij, the component of the stress, is equal to the derivative with respect to epsilon ij of rho e. Now I want to do a clarification. The density is for an elastic, for a flexible body, is a function of the deformation. Should be. If you deform a body, the density should vary. But this kind of variation is a higher order, and this could be demonstrated to be. For this first order level we are talking about, we consider the density practically equal to this. So it's not dependent on the strain at all. And therefore, in the definition here, this variable can be put inside and outside the derivative. Okay? So take this, and what happens? The derivative of the constant is of course 0, and then we have to derive the 0 plus the derivative of, with respect to epsilon ij, of a. We should use another couple of index, so use lm, epsilon lm, plus 1/2, and here we have the derivative with respect to epsilon ij, and then inside here again another name for the index. You can use epsilon lm, b lm, and then rs and epsilon rs. I am voluntarily using this index, this like this, and this like this. At the end of this summation, we have a number after the summation, and we have to derive this number with respect to this variable. Okay, and the same here. What is the result of this derivation? Here, for example, here we have a11 epsilon 11 plus a12 epsilon 12 and so on. When you derive this summation with respect to epsilon ij, the only term surviving is aij. Okay? If you do the same here, you have to derive a quadratic form. And the rule for deriving a quadratic form is the following. You have to first derive this term in this position, and then keeping the other constant, and then derive the second term, keeping the other constant. But please, what about B? B are representing partial derivative. B, remember, B, Lm, Rs is the second derivative of rho E, first time with respect to epsilon m, second time with respect to epsilon Rs, evaluated at zero deformation. And what about this second order derivative? If the second order derivative is a second order derivative correlated to a continuum function of the strain component, the existence of this function implies the fact that you can exchange the order of the second order derivative, so obtaining the same quantity. And this is also known as Schwarz theorem. So the existence of the elastic energy exists a elastic energy, a volume, imply for the Schwarz theorem that B Lm is equal, B Lm Rs is equal to B Rs Lm. So you can exchange this index because you can exchange the order of the derivative. And therefore, if you take this partial derivative of this quantity, if you use this symmetry in B, you have identical term of type. You have this, the following. You have the following. You have B, Ij, Lm, Lm epsilon Lm, plus B, Rs, Ij, epsilon Rs. Excuse me. You have this. But Bij En, when Lm, when you sum in Lm here, this sum this, and when you sum this here, this with this, you can exchange the role of the index, and therefore you are summing essentially the same quantity. Okay? And so you have that Tij is equal to B Ij Lm epsilon Lm plus A Ij. The conclusion, if you consider an elastic body, and you consider a second order expansion of the elasticity function of internal function rho E in the neighborhood of an undeformed configuration, you have, and if you consider the definition of elastic body, the consequence is the following. The consequence is that Tij is equal to Bij Lm epsilon Lm plus Aij. Okay? So, if you assume that you have zero stress for zero deformation, so if you assume that you don't have preload in your body in the undeformed configuration, that you have tau Ij equals 0 for epsilon Lm equals 0, then this term can be cancelled, and as a consequence, for having an elastic body, in the linearized configuration, you have that tau ij is equal to b ij lm epsilon lm. This kind of comment is completely uncorrelated with the constitutive relationship. In fact, one can say, oops, but this is a linear relationship, just what I have found characterizing the material in a constitutive point of view. But we assumed for linear elastic, no, not linear elastic, but we assume for linear constitutive relationship, this fact that T tau ij is equal to C ij lm. Oh guys, this is not a trick. These two relations are derived in a two independent way. The constitutive relationship is a fruit of experimentation in a lab by an engineering, performing the tensile and stress test on the material, and then found a C parameter, like the Young modulus, the Poisson, everything, okay? This is an experience done for characterizing the material, point, okay, period. This kind of consideration here is another story, independent story. We are supposed to have an elastic body with small perturbation. I consider expansion of internal energy, and that's the coefficient of the expansion. And because of this definition of the coefficient of expansion, I have that in the case of the elastic body, tau is equal to b ijlm epsilon lm. Now, putting together this information, which is a thermodynamic information given by the existence of internal energy, plus this experimental engineering information characterizing the constitutive nature relationship between stress and strain, I have to accept that this C ij lm has to be identical to B quantity bij lm, but please attention, bij lm represents a second order derivative, and this information can be translated to C. So C has to be symmetric as B is symmetric. Okay? Okay? I hope to have given to you this concept in an honest way. So, thermodynamic, elasticity, linearized elasticity. By considering linearized elasticity, I have that necessarily tau is equal to b ij lm epsilon lm, and b is representing a second order derivative. Therefore, bij lm is equal to b lm ij, and this is the consequence of this symmetry. Period. Another fact, in the laboratory, I am able to find a linear relationship between stress and strain. And these are the engineering constants characterizing the material. Young modulus, Poisson, blah, 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 blah. Comparing these two facts, you have to conclude that your engineering quantity evaluated in the lab has to respect a symmetry if you want to suppose the existence of an elastic energy. Okay, so the conclusion is this: B is the same fact, is the same matter like C, and since B is symmetric, then C is symmetric. Symmetric. And therefore,Cijkm, our constitutive law or Hooke law for anisotropic material in general, is equal to Ckmij. And that's all. This property is a consequence of existence of the function rho e as a function of the stress tensor or strain tensor. Existence of this is the state space state equation for elastic solid. Also in solids mechanics there are state equations. And this is the state equation for elastic solid. A function mapping the internal energy as a function of the deformation. So, if you have this function, if you're supposed to have linear transformation, we have concluded that rho e is equal to 1/2 epsilon ij c ij km epsilon ij. Oops, but this is the stress tensor. Oops. And so rho e is equal to 1/2 epsilon ij t ij. Oops. This can be written also as 1/2 t double dot e. And this is an absolute notation for expressing this. Okay, so the famous 1/2 of the elastic energy is a 1/2 arising from a Taylor expansion. Ladies and gentlemen, remember this. Is a term arising by the second order term in the Taylor expansion when you have 1/2 multiplied by a second order derivative. And because of the symmetry of the second order derivative, I mean the Schwarz theorem, you can derive the symmetry index of the constitutive tensor Cij Km Ckm Ij. And this is the tale, this is the story of the linear elastic body for you. Okay, this is the main result, useful for us for expressing now E in the case of elastic body. We have this quantity equal to tau ij epsilon ij, summation in ij. Okay? Now we are ready for express this quantity as a function of Q. How can we do? Why? Because we have to derive this quantity for this C term. What is C? What is C? Okay, here. We want to express this B term, this B term here. So we have to express E as a function of Qn. And how can I do? It's easy. Now we have to remember that epsilon ij is equal to the derivative 1/2, of the derivative of ui with respect to xj plus the derivative of uj with respect to xi. In a word, we have the symmetric part of the gradient of the displacement. We have this, and we have, of course, that u is equal to summation of u is a summation of psi n qn, and that's all. These are the steps to be performed to reaching the final formula. So the final formula, E is equal to half integral of Cij Km epsilon ij epsilon Km. And remember that this and this is tau ij dv. So we're 1/2 integral of C ij Km, and for epsilon ij I can write u first I component derived with respect to j. Okay, this is the symbol for the partial derivative with respect to xj. Okay, plus uij divided by 2, and this is the epsilon ij, the symmetric part of the gradient of u. And the other epsilon component is almost the same, but we have to use uk common m plus um common k divided by 2 dv. Now we have to substitute this. We have to consider that u can be expressed through the shape function and q. Remember that in the finite element practical discretization, these shape function are the so-called temp function, as I told you the day before yesterday, and the q quantity, qn, are representing the displacement in the node. Okay, so I have to substitute this here, and I have the following. At this point, I have a very, very relevant, interesting point for you in the footnote here. I, J, K, M, L, are all physical index running from 1 to 3 maximum, the space. Okay? This is important. But in this other summation, guy, here, n, like, please use S, 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 S. S here is running from 1 to the last index for the finite element degree of freedom. So currently these index are numbering the degree of freedom of your finite element model. So these index are really not physical index, but associated to the specific body discretization considered. Okay, and therefore we have that R, S, P, Q. I use this strange index just to stress this point. Is from 1 to 13,247, which is the number of degree of freedom of your model. Number of degree of freedom of your finite element model. Okay, it's something artificial. Okay, so substitute this here, and you have C I J K M. Instead of this U, you can introduce a summation for R quantity, and here you have psi R function. This is a shape function R, component I derived with respect to J plus psi function R, J component derived with respect to I, divided by 2 and multiplied by QR. So this summation is epsilon ij. Okay? Note that I have indicated this summation. I don't have indicated summation with respect to the physical index ijkm. I have supposed to sum with respect to this, but I have not indicated this summation with respect to ijkm and the physical indexes. Okay. And next, the other quantity, epsilon km, can be represented like a summation, and an independent summation with respect to the other. We have S here, and we have size S, again, km plus psi S ms divided by 2 and multiplied by qs. Finished. This is epsilon km, and this is integrated by in dv. Okay. Note that our new variable q, r, and qs are not dependent on space, are only dependent on time. So we can move this quantity together with the summation out of the volume integral outside, and we can write the following. Yes, equal to, I like this 1/2 in evidence, and we have a summation R and a summation together RS, and we have QR, QS from 1 to 30,247. This is just to stress the fact that this summation is a summation in all the degree of freedom of your model. And at the end here I have this quantity, interesting quantity, which is the integral. I have 1/4. I have psi r ij, so plus psi r j I c I j k m psi s km km psi s m comma k in dv. Okay, so once you sum all this index I, j, k, m, I have a quantity, a final quantity, a very final quantity, depending on, do this integral, and you have a quantity like k or s. If you fix r and s and you sum this quantity, remember that inside here you have to sum the physical index. You have to sum I, j, k, m. In order for, so you have 3 to the power 4 operation to be done. Okay? For you perform this operation and you obtain a number for any RS. This number is part of a table. This table is an engineering matrix, and this engineering matrix is also known as stiffness matrix. Okay? What is this? Okay. Stiffness. Question: is this matrix symmetric or not? Remember that the previous matrix, the mass matrix, was symmetric in a natural way, because in the definition of mass matrix here, we have a dot product between the shape function here, this by this, so you can commute the product and you have the same term for the property of the dot product. But here we don't have a dot product, we have a complicated relationship. But is this relationship symmetric? The answer is yes. KRS is equal to KSR, I mean is symmetric, because Cij, another story, continuum mechanic is another, but Cij is symmetric in the sense that Cij is equal to Kmij. And this is symmetric because the elastic energy exists because of the existence of the elastic energy for linear solids. And this is the very, very important concept of the elastic body. Ladies and gentlemen, this is an elastic body. An elastic body is a thermodynamic definition related to the existence of the elastic energy, but this thermodynamic definition as translated to a discretization process produces the stiffness matrix, which is a symmetric matrix, as Cijkm is symmetric as well. So, and this consequence, you can see this consequence here. Look, what I state is very simple, because if you see this dependence by R, you have R here and you have S here. Through the shape function, there is a correspondence between the R index and the Ij index, and there is a correspondence between the S index, the unphysical, and the Km index, the physical one. You have this correspondence, this relationship, through the space function, the shape function. And so, since you can invert Ij with Km, in the same way you can say that you can invert R with S. And this is the story of the elastic body in terms of stiffness matrix. Okay? So at the end of the story we have the elastic energy is equal to Q transpose KQ. Another quadratic form, and if this quantity can be defined like positive, necessarily kappa, K matrix, is positive in the same sense of the mass matrix. Okay? What about the last point is, what about the point here is the point B. What about the derivative of E with respect to Qn? Which means, what about the derivative with respect to Qn of 1/2 Q R K R S Q S double summation in R and S. Again, another quadratic form. You have to derive with respect to this first, keeping this constant, and then derive with respect to this, keeping this constant. You should obtain, by taking this derivative, you should obtain N S Q S summation in S plus K R N Q R summation in R. This is the result of, you have 1/2, this 1/2. So you have to sum this, and then you have to sum this. Are these two summations identical? Yes, these two summations are identical because the matrix is symmetric. And therefore, the final result is that this term is equal to K N S Q S. Okay? And therefore, the Lagrange equation of motion are given to you M Q dot dot A term plus K Q the B term equal to a strange quantity known also as E, to be explored. To be explored in the next hour. Okay? Stop. I'm sorry for this delay, but I started the lesson with a bit delay, and therefore. Okay, thank you. A pause now.